Good morning, students. Today we shall begin with a new chapter. We are studying 13th chapter. Name of the chapter is Nuclear. We are learning about a nucleus in this chapter. Some terms like binding energy, mass defect, nuclear forces, nuclear energy. So this is a descriptive chapter. You don't have any rigorous mathematical derivations in this chapter, so you can very easily learn this chapter. And some portions of this chapter is deleted, that is radioactivity is deleted and the binding energy curve is also deleted. So let us begin with the chapter Nuclear. So all of you are knowing the structure of an atom. An atom consists of a central core around which electrons revolve in different orbits. This central core of the atom is called as the nucleus. The entire positive charge of the atom and almost the whole mass of the atom is concentrated inside this nucleus. So what is a nucleus made of? A nucleus is made of protons and neutrons. So these protons and neutrons are together called as nucleons. So if you say the word nucleon, you mean either it is a proton or a neutron. Now, how to represent a nucleus? Let us take a nucleus X. A nucleus X is represented by two important numbers. One is Z, that is called as the atomic number. Another is A, it is called as the mass number. X is the chemical symbol of that nucleus. So ZXA represents a nucleus X. So you are knowing about this atomic number and mass numbers in chemistry. You are already aware of this. Now let us revise the same once again. Z is the atomic number. So Z gives you the number of protons inside the nucleus. Then let us say in the nucleus there are n number of protons. Let us say capital N stands for number of neutrons inside the nucleus. Then what about the mass number? The mass number gives you the sum of protons and neutrons inside the nucleus. That is A is equals to number of protons plus number of neutrons. So A is equals to number of protons is Z, number of neutrons I have denoted as N. So A is equals to Z plus N. So what will be the value of N? N is equals to A minus Z. So the number of neutrons is the difference between A and Z. So if you take A minus Z, mass number minus atomic number, you will get the number of neutrons inside the nucleus. So let us apply this for a particular atom. Let us take an example of a very simple nucleus 3Li7. This is a lithium nucleus. So 7 is the mass number, 3 is the atomic number. So I have written it here. Z is equals to 3 and A is equals to 7. Now I want to find out how many neutrons are there inside the lithium nucleus. So the number of neutrons, as you know, N is equals to A minus Z. So put the value of A and Z. A is 7 and Z is equals to 3. So 7 minus 3 is equals to 4. So how many neutrons are there? 4 neutrons are there. And how many protons are there? That is nothing but the value of Z. Z is equals to 3. So it contains 3 protons and it contains 4 neutrons. So to find out the number of protons and neutrons is very necessary when you are solving a problem on this chapter. So when you are calculating the binding energy, you should know how many protons and neutrons are there in a particular nucleus. So you should know this method of finding out number of protons and number of neutrons inside a nucleus. Now let us classify the nuclei in different types. I have taken 3 types here: isotopes, isobars and isotones. Let us define each one of these. Let us take the first one, isotopes. These are the nuclei with same Z value but different A. Meaning is they have got same atomic number but different mass numbers. Let us take an example. Let us take the hydrogen isotopes. 1H1, 1H2 and 1H3. This is hydrogen, deuterium, tritium. So if you observe these examples, what do you find? They are having the same Z value. One is common. So Z remains the same. What is changing? The mass numbers are different. 1, 2, 3. So these nuclei are called as isotopes. So what is the definition of isotopes? These are the nuclei with same atomic number but different mass numbers. So the meaning, what is the meaning of same Z? Same Z. Z gives you the number of protons. So all these nuclei, they contain the same number of protons. And you know that chemical properties of an element depend upon the value of Z. Because Z is same for all this, they have got same chemical properties and they occupy the same position in the periodic table. And therefore they are nuclei of the same element. H is common here. So these nuclei represent only one single element. They are nuclei of the same element. Now let us come to the next one. Isobars. Let us reverse these two. So these nuclei have got same mass number but different atomic numbers. I have interchanged Z and A. So let us take an example. 1H3 tritium and helium 2He3. What do you find here? The mass number is the same, equals to 3, but the atomic numbers are different, 1, 2. So these nuclei with same mass number but different atomic numbers are called as isobars. So they are having same A. What is A? A gives you the number of nucleons. So all these isobars, they are having the same number of nucleons. Now let us go to the third one, that is isotones. So here this is same Z, this is same A, but here both are different. They are having different atomic number and different mass number. Then what is same for this? Number of neutrons is the same number of neutrons, and N is equals to A minus Z. So the nuclei with same number of neutrons but different atomic and mass numbers are called as isotones. Let us observe the example. I have taken tritium here, 1H3, helium 2He4. So here atomic numbers are different, mass numbers are also different. But what is same? Number of neutrons. Number of neutrons means A minus Z is same. What is A minus Z here? 3 minus 1. So it contains 2 neutrons. In this helium, 4 minus 2. So it also contains 2 neutrons. So number of neutrons remains the same. Such nuclei are called as isotones. So let us summarize it once again. Isotopes contain same number of protons. Isotones contain same number of neutrons, whereas isobars contain same number of nucleons. Nucleons means protons and neutrons together. Now let us go to some important units that we use in atomic physics. So usually in the SI system, length is measured in meters and mass is measured in kilogram. But these units become too large for atomic dimensions. So to measure atomic distance and the masses of atomic particles, we use smaller units. So the unit of length in atomic physics is Fermi. It is named in honor of the scientist Enrico Fermi and it is denoted by the letter Fm. So Fermi is the unit of length we use for atomic physics. So what is the relation between Fermi and meter? I have written it here. 1 Fermi is equals to 10 raised to minus 15 meters. So this is a smaller unit of length. Now to measure the masses of these atomic particles, we use a unit called as atomic mass unit and it is denoted as U. So how to define one atomic mass unit? One atomic mass unit, 1U, is 1 by 12th the mass of one carbon atom. Carbon atom is 6C12. You take the carbon atom, find out mass of one carbon atom, divide it by 12, you will get it as 1U. Now if you put the value of the mass of one carbon atom and simplify, you will get the relation 1U is equals to 1.66 into 10 raised to minus 27 kg. So this is the relation between U and kg. So you should remember these values They are useful for solving the problems. You have to convert usually from kg to U or U to kg. So you should know this relation from the problem's point of view. So these are the two units we are using here. Fermi for measuring the distance and atomic mass unit for measuring the masses of atomic particles. So let us revise the points we have done now. What is a nucleus? It is the central core of an atom in which the entire positive charge and almost the complete mass is concentrated. It consists of protons and neutrons together called as nucleus. It is characterized by two important numbers. One is the atomic number Z, another is the mass number A. Atomic number gives you the number of protons and the mass number gives you the number of protons plus number of neutrons. Therefore, number of neutrons is always equals to A minus Z. Then we have distinguished between three important nuclei: isotopes, isobars and isotones. What are isotopes? Nuclei with same atomic number but different mass numbers. What are isobars? Nuclei with same mass numbers but different atomic numbers. And what are isotopes? These are nuclei with same number of neutrons and different atomic and mass numbers. Then we have defined two smaller units for length and mass. The unit of length we have taken as Fermi. 1 Fermi is 10 raised to minus 15 meters, and the unit of mass we write it as atomic mass unit denoted as U, and the relation between U and kg is 1 U is 1.66 into 10 raised to minus 27 kg. We shall now find out the energy equivalent to a mass 1 U. For that, we shall make use of Einstein's mass energy relation E is equals to mc square. What is this relation? In classical physics, mass and energy are considered as two separate physical quantities, and there are two conservation laws, one for mass and the other for energy. In the year 1905, Einstein, from his special theory of relativity, showed that mass and energy are two forms of the same quantity. He gave the mass-energy relation as E is equals to mc square or m is equals to E upon c square. So what is the meaning of this relation? Mass and energy are equivalent. The energy equivalent to a mass m is given as E equals to mc square. The converse is also true. The energy E is equivalent to a mass m equals to E upon c square. What is c here? C is the velocity of light in vacuum. So using this relation, we shall find out energy equivalent to a mass 1 U. Just now we have shown 1 U of mass is equals to 1.66 into 10 raised to minus 27 kg. Also, in the second chapter, you have learned that 1 electron volt is equals to 1.6 into 10 raised to minus 19 joule. And if you want to use a higher unit, it is million electron volt or mega electron volt. So 1 MeV is equals to 10 raised to 6 electron volt. So we shall make use of all these relations to find out now the energy equivalent to a mass 1 U. So we shall begin with the Einstein's mass energy relation. E is equals to mc square. So here mass is given. What is the mass? Mass is 1 U and you have to find out the energy equivalent to a mass 1 U. So let us put mass m as 1 U. We shall write in kg. It is 1.66 into 10 raised to minus 27. So I have taken it up to 4 digits for accuracy. So it is 1.6605 into 10 raised to minus 27 kg. The velocity of light in vacuum is 3 into 10 raised to 8. You have to take the accurate value up to 4 digits. So I have taken it as 2.9979 into 10 raised to 8 meter per second. So let us put the value of m and c in this equation and find out the energy. So E will be equals to the mass value I have put here 1.6605 into 10 raised to minus 27 into c square. C is 2.9979 into 10 raised to 8 whole square. If you simplify this, the value comes out to be 14.924 into 10 raised to minus 11 joules. Joule is the SI unit of energy. Now, from joule, we shall convert it to electron volt. So many joules, that is 1.6 into 10 raised to minus 19 joules is 1 electron volt. So, 14.924 into 10 raised to minus 11 joules is how many electron volts? So, you have to divide it. So, E in electron volt will be 14.924 into 10 raised to minus 11 divided by 1.602. 02 is taken for accuracy. 1.602 into 10 raised to minus 19 electron volt. If you simplify this, you will get it as 931.5 into 10 raised to 6 electron volt. But 10 raised to 6 electron volt is 1 mega electron volt. So you can write this as 931.5 MeV, mega electron volt. So what is the result? 1 U of mass is equivalent to 931.5 MeV of energy. So this is a very important relation. In the problems on nuclear, where you have to find out the binding energy or you want to find out the energy released in a nuclear reaction, we are directly making use of this relation. 1 U is equivalent to 931.5 MeV of energy. So this is a very important relation, and we have got this relation using Einstein's mass energy relation. So let us summarize what we have done now. According to Einstein's mass energy relation, energy and mass are equivalent, and we have the relation as E equals to mc square, where c is the velocity of light. Using this relation, we have converted 1 U of mass to energy. So we have used the Einstein's relation E equals to mc square. We have put the value of m as 1 U. Putting the value of m and c, we got the energy E equals to 931.5 MeV. So the conclusion is 1 U of mass is equivalent to an energy 931.5 MeV. So this is all for today's session. Thank you.